Professor, I have a quick admin question.
Yeah, hello.
Hi. So I know we don't have class next Monday because it's a holiday, but have you decided if we're going to have a lecture on Thursday?
It's great that you're asking because it's my first year in Canada. So what holiday, actually?
It's Family Day.
Family Day.
Yes, it's actually a province-wide thing. So Monday is Alberta, BC, New Brunswick, Ontario, and Saskatchewan.
Oh, thank you very much. Thank you very much for telling me. And what is Family Day?
A day to spend with your family.
But my family is under quarantine in a faraway land.
But it's actually a fairly new holiday. I think it was added just a few years ago. I can't remember. I remember when it first was introduced, so I know it's not that old.
So you're saying there is no lectures on Family Day?
I think the university is closed, actually, technically. Well, I can check for you, but
no, I'll check. I'll check. Okay. Okay. Yeah, I did look at the beginning of the semester. There's a spreadsheet or something with all the holidays.
Yeah.
But I don't remember seeing a Family Day. Maybe I just ignored it because this. Okay. Yes, it does. Unfortunately, you won't be creating such beautiful pictures in the homework. I did try to make the homework so that it would create such beautiful pictures, but it's actually a bit non-trivial, apparently, to do like deep net visualizations that, look as good as this one. Non-trivial. And your other question, Luke, was about
Thursday, because it's reading week next week, but I think for grad courses it's technically up to you.
Oh, it's next week. Oh my god. Okay.
Yeah.
So you call it reading week, right?
Yeah, but it's mostly an undergrad thing as far as I understand.
I did not make it by myself. I just took it from the internet, actually. I borrowed it from the internet. But there is a website where you can upload your own pictures. And in those, basically, it modifies your picture to look, more psychedelic. So, Luke, thank you for reminding me about both of those things. I'll send an email with the clarifications about both of these. So it's basically a question about next week, Monday and Thursday, right?
Well, Monday the university's closed, so yeah. I don't think there's classes for anyone.
Okay.
But Thursday, I think it's up to you.
Okay.
Yeah.
Okay, so let us start. So welcome to Deep Learning Theory and Data Science. Today we're continuing our discussion about the max margin implicit bias of gradient descent on separable data. Zangan is making sure I don't forget to remind everyone to like and subscribe. You might have noticed that the website has undergone some changes to highlight, to remind everyone who passes through it to like and subscribe. Just give me 1 second to pull up my slides. Okay, so, right, so in the previous lecture, we started discussing the implicit bias of gradient descent on separable data, and we saw this theorem which is saying that if you are running gradient descent on a linearly separable data set of data points and labels with the exponential loss. And if your step size is small enough, then you will converge to what is called a max margin classifier, right? And if you remember this quantity right here, we discussed how that is the margin of the ith example. And here we're calculating the minimal margin over the whole data set. And the lim of t going to infinity is essentially corresponding to t is basically the step of gradient descent. So after many steps of gradient descent, the margin is going to be equal to the optimal possible margin. So you're maximizing the margin, right? You're maximizing over W2 less than 1. Now, I believe Luke actually sent me an email asking how come there is no division here by the L2 norm, right? And the reason is, I wanted to reiterate because it was a great question. The reason that you don't divide here by the L2 norm of W is because W is restricted here to a unit L2 ball. And so instead of dividing by the L2 norm, you just restrict its norm. And in practice, what's going to happen is that you can actually show that this maximum is going to be attained for a W where the L2 norm is equal to 1. And so you don't actually need to divide by the L2 norm of W. Karen is asking, does this theorem guarantee convergence or just what the limit is in the case of convergence? It guarantees convergence. It guarantees convergence because it says that in the limit, your margin is going to be the optimal margin. So it does guarantee convergence. I guess another thing you could ask yourself, maybe that's what you mean, is the loss decreasing with time? Because there is an exponential loss. And you can actually prove that the loss is decreasing. You can prove that. So after we saw this theorem, we tried to understand what is a max margin classifier through beautiful drawings made by other people. And today, what I'm going to do is go over the argument for how to prove this theorem, how to prove it. So in order to do that, let us first look at some basic definitions. So first of all, recall the exponential loss. The loss depends on the classifier W, and it's equal to the sum over all the examples from I equal to 1 to n of the exponent minus yi wxi. So this is just the definition of the exponential loss. If you don't remember it, just accept it, but as a definition, okay? Now, there's a strange thing you can do here, which is you can assume without loss of generality that all the labels yi are equal to 1. Now, why can you assume that? Does anyone have any thoughts? Why would that be a thing you can do? Why can you assume that without loss of generality? Because the data is linearly separate. There is a simpler statement you can make. Yeah, exactly. So essentially what Jim Shaw is saying is that you can make the xi negative. So essentially imagine you have a set of data points, let's use blue, which are, you know, xi. Let's say x1 is equal to x1, y1 equal to 1, then you just keep it as is. If x1 has a, if x2, sorry, has a y2 equal to -1, then you can just redefine x2 tilde equal to y2 x2. So you essentially, you can flip all the negative examples with a minus. Another way of saying it, maybe I can say it in a clear manner. So another way of saying it is, notice that the only thing that matters here is what is yi multiplied by xi, right? And so if yi is positive, then this is equal to xi. If yi is negative, this is equal to minus xi. So you can just redefine all the negative xi's, all the xi's which have a yi equal to -1, you can just absorb the minus into the xi, right? What if that destroys linear separability, asks Tristan. It cannot destroy linear separability, because if you have only positive points, then they're linearly separable, right? Because like the word separability is trivially, if you just have all points equal to one class, it's trivially separable. But this is just a trick for making the expressions a bit easier to work with. It's just a trick, okay? If you think about its implication for linear separability, it will confuse you. So don't think about it, you know? If something confuses you in life, you just ignore it. And then life is simple. So is it clear that you can absorb yi into xi? Is that clear? Kind of clear? How can I make it clearer? So essentially, if you have an example xi, which has a label y equal to -1, you just replace that example with minus xi and y equal to +1. And then all the examples are with a label +1. Does this make more sense, Gina, or other people? Yeah, you just manually replace it. Yeah. Okay, so now the loss is slightly simpler. It's just W inner product xi, sorry. Okay, so the next thing we need to do is we need to calculate the gradient, because we're doing gradient descent. So gradient seems like a quantity that is of interest. So how does one calculate the gradient of this function? And gradient with respect to what? So since the loss depends on the classifier W, we want to calculate the gradient with respect to W, right? So how does one calculate the gradient of exponent minus inner product Wxi? So it's simply equal to, you derive exponent with respect to the thing inside, right? So the derivative of an exponent is just the exponent multiplied by the inner derivative. And what is the inner derivative? It's just minus xi, right? Because the derivative of an inner product is just, you know, the xi. So this is what you can see here. This is the x, right? And this is the inner derivative minus xi. Okay. Now notice that this quantity is simply the loss, the exponential loss of the ith example. It is a scalar, and we can actually write this as minus xr, where x is a matrix which contains in its columns the examples xi, and r is a vector which contains in its entries the loss. So here's how it goes. You have a matrix here which contains in the columns, each column is a different xi, right? This is xi, multiplied by a vector r, which contains in the entries the loss of the ith example. Does this make sense? So why do we want to do it? Because people like matrix vector multiplications, right? Do you like matrix vector multiplications? I love them. Okay, it seems like there's other people who love them. Now, the next thing that we want to do is notice that this vector R satisfies a property, and the property is that the L1 norm of R is equal to the loss. Why is that? Why is that? Why is the L1 norm of R equal to the loss? Just by definition, because R is a vector which contains in its entries the losses of the different examples, and the L1 norm would just sum all of these losses to create the total loss, right? And the loss and the experts are all positive. That is correct. Yes. Yes, 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 yes. The next thing that we're going to do is we're going to calculate the Hessian matrix, because that's going to be also important in our proof. So how does one calculate the Hessian? You just calculate the derivative with respect to W again of the gradient. So if you look at this expression, and if you try to derive it with respect to W, what do you get? So this quantity does not depend on W, right? So you leave it be. And then you derive this quantity. So what's the derivative of this quantity with respect to X? It's just the X multiplied by minus Xi, right? And then you get X minus Xi, and the minus is, canceled with this minus. So you get Xi transpose. Okay, makes sense. Okay, so notice that this again, exp is simply equal to Ri. So this is a sum over Ri, Xi transpose. So it's a weighted sum of outer products. Okay. So these are the basic definitions, ingredients needed for the proof. Another thing that we need is where does the transpose come from? So, right. So one answer, which maybe you won't like, is, if there were no transpose, then this would make no sense, right? You cannot do Xi multiplied by Xi because they're vectors. So the only other thing that there could be is Xi inner product with Xi. But that would give us a scalar, which doesn't make sense because the Hessian, the second derivative, has to be a matrix. Does this answer the question, Jin Hui? Or no? I guess it is not a proper answer. It's not a proper answer. If you want to do this, very properly, you could just do the derivative of the loss with respect to Wi, derivative with respect to Wj, and just write what it's equal to, right? It's just that would take a lot of time. And we're unfortunately impatient people, right? So the next thing that we need is some concept called duality. Duality is something you encounter often in convex optimization. Does anyone have students seen duality in their past life? Do they love duality? Do they have affection to duality? Love it? Wow, okay. In a different class. Okay, so I won't go too much into the intuition behind duality because I have a feeling that it might drift us away from what we want to do. So I'll just define duality, just the definition of duality. If someone would like to know what's the intuition behind duality, I can explain the intuition behind duality at the end of the lecture, okay? Because I don't want to go on a tangent, so to speak. which is a joke about duality, by the way. Okay, so what is the what is the definition of duality? So assume you have a function f, then its dual function f star, star is stands for dual, is defined as function of y. So originally you have f of x, the dual is f star of a different variable called y, and the dual is defined as the supremum over R of y inner product R minus f of R. I guess in this case, this should be R, f of R and f star of y. So it's the supremum over R of y inner product R minus f of R, okay? Just definition. Yes, it can take values in infinity, we'll see that. So this is the definition, and oftentimes it is called Fenchel conjugate. Fenchel is a person. Now, there is a theorem which is called Fenchel duality. And this theorem says that if you have two functions, f and g, which are convex functions, and they have conjugates, which are denoted by f conjugate, g conjugate, then the infimum over R of fr plus gxr can be lower bounded by the supremum over w minus f conjugate x transpose w minus g star minus w, which looks like a very unpleasant theorem, doesn't it? But let me try to explain what is this saying. This is essentially saying in optimization, you oftentimes see problems which are annoying to solve. And many times what you do is, instead of solving the primal problem, which is the original problem, you convert it to a dual problem. So here you can see this is the primal problem, which requires you to minimize something. And instead of solving that, you solve an alternative problem, which is called a dual problem. The dual problem requires you maximizing something. Now, in this case, I'm writing inequality, but many times the problems are actually related by an equality. So solving one is equivalent to solving another in some sense. Now, there is an intuition for what is the relation between the primal problem and the dual problem. And there's many examples of, primal problem and dual problems, but we don't want to go into that. Let's just accept this as a theorem, okay? As a theorem. By the way, what kind of this is the type of, this type of theorem you see many times in math. This is the, how is it? 1 second. I forgot there is a name for this type of inequalities in general. You see them in many different parts in math, not necessarily in optimization. When you have the infimum over something is greater or equal to the maximum over something. The name escapes my mind. Settle. No, I was thinking of a different word. Different word. Not sandwich. No, not sandwich. Never mind. So at this point, I want to switch from the presentation to a document where I'll continue with the proof. Okay. So hopefully I remember the proof. Right. So the first thing that we want to do is we want to look at the gradient of the loss of W, L2 norm, divided by the loss of W. Why are we looking at this quantity? You might ask yourself. The reason is going to become clear later, but this is a fundamental quantity in the proof, okay? So notice that the gradient of the loss is equal to, what is it equal to? It's equal to XR according to what we've said 5 minutes ago, right? So this is XR L2 norm. And the loss is equal to the L1 norm of R. Does everyone agree with this? Yes. Now, notice that you can write that this thing is actually greater equal than, let's say, the supremum or the maximum over R of XR. Oh, let me actually switch the order of an indicator function which says that the R has an L1 norm equal to 1 and that the R is positive plus the L2 norm of XR. Why is this correct? Because this is just a very strange. Okay, so first of all, what is an indicator of a set? So if I write 1s, indicator of set, it's equal to, oh, sorry, I should have written minimum. So it's infimum here. My bad. So an indicator of a set is equal to 0 if X is in the set, and it's equal to infinity if X is not in the set. Have you seen indicators in your life? Do you like indicators? No? I remember, the only thing I remember from probability is indicators. You don't see a lot? Okay, no, okay. So an indicator is, as the name suggests, indicating if the input is in a set. Okay, so if you want to, what's the intuition behind this transition here? The intuition, you've only seen them as outputting 1 or 0. Oh, by the way, this can be written as equality. So what's the intuition behind this equality? The intuition is that the only way for this infimum to happen, or the only way for this infimum to be not infinity is if the condition is satisfied, right? So the only way to minimize this function is if the L1 norm of R is equal to 1, and if R is greater or equal than 0, right? But notice that here, we know, essentially here, you're forcing R to have an L1 norm equal to 1, right? And also we know that R is greater or equal than 0 by definition. Does this make sense? Maybe I should repeat it. So essentially, the idea behind this transition is that because here you have R divided by its L1 norm, you know that the L1 norm of this quantity is equal to 1, right? Because you're dividing this by the L1 norm. And also, you know that the R's are positive, right? So if you know that the R's are positive and their L1 norm is equal to 1 essentially, then you might as well just write infimum over indicator plus, you know, the XR L2 norm. Does anyone have any questions about this step? This might be the strangest step of all of them. But this is actually a very common thing to do in optimization, writing this type of illogical, you know, it's not illogical, like strange, I guess, statements. Any questions? Why is the L1 norm of R1? Because essentially you're dividing here by its L1 norm, right? So if you're dividing here by its L1 norm, it's equivalent to saying that the L1 norm is equal to R. You know, we could have said here like R wiggle or something like that. R wiggle. Why do I write infimum instead of greater equal? Because the infimum, like if you think about it, the infimum is just saying that we're forcing, oh, I should say greater equal. Yes. You're correct, yes. The reason you need the greater equal is because you are allowing R to be anything that satisfies these properties, right? The property of positivity and the property of L1 norm equal to 1. And so in here, you could have had any sort of R you might imagine, right? Okay, are there any other questions? Any other questions, complaints, concerns, issues? For those interested, this is Folland page 154. Huh. Basically, this is without loss of generality. Why is it plus instead of times? Because we want plus, because plus is going to be more useful. I guess you could have used the times as well, but we need a plus here. So if you want to read about duality, so you can look at I like Boyd's book, but there's other books as well. There's Rockefeller, but anyway. So at this point, what would you, I think plus makes a lot of sense, as you will see next. So at this point, what should be the next step? Do you have an urge to use some lemma or a theorem now? Do you see here a theorem that can be invoked? A theorem that you might have learned just 2 minutes ago. Fenchel, exactly, yes, that is correct. So at this point, what we would like to do is write that this is the supremum. So essentially, we're gonna call this thing is going to be f of r, right? And the other thing is going to be g of xr, okay? Let me remove the tildes. And we're going to show that this is greater or equal to minus f conjugate xr minus g conjugate, oh, sorry, this should be the conjugate variable, which is w, where we're doing the supremum over w. Why did I switch a color in the middle? Makes no sense, but okay. Does this make sense? So we just invoke the Fenchel duality theorem. Now, in order to continue, what do we have to do at this point? What's the next step? Trying to make this an interactive proof where you prove it instead of I. I just give the ever so slight, what's the word? Small hints, yeah. So Gina says calculate the dual, and Gina is correct. You need f and g to be convex, that is correct. So we want to find the dual functions. So let us find the dual functions. So what is f? What is the definition of f? F is defined to be an indicator, right? So f of, let's say, z, sorry, so f star is going to obtain the dual variable, let's just call it z, and it's going to be equal to what? To the supremum of, and then you have z inner product with some, let's say, r minus f of r, right? This is just by definition of the Fenchel dual function. Now, what should we do next? We should just plug the definition of f, right? So f, what? It is the indicator. So if I plug now the definition of f, I get 1, L1 norm is equal to 1, and R is non-negative. By the way, there is a fancy name for this thing. Does anyone know what's the fancy name for this thing? When I say fancy name, I mean, you know, how people on the streets would call it. Yes, a simplex, exactly. This is a simplex. If you want to impress your friends, use the word simplex. They'll be impressed. So at this point, we want to solve this supremum. So notice standard. Why do you have to insult it by saying it's standard? Just don't say it's standard. So at this point, notice that, I'm just kidding. Notice that this is equivalent to, it's fancier, exactly. So notice that because we're trying to do a supremum, and there's a minus here, and this becomes infinity when we're violating the indicator constraint. So what is this equivalent to? It's equivalent to forcing this to happen, right? So it's equivalent to saying supremum over R, which has an L1 norm equal to 1, which is non-negative, of Z inner product R, right? Because if you had an R which violated the constraint, which wasn't in the set, then this thing would be infinity. So you'd get minus infinity, and minus infinity would never achieve the maximal value of the optimization problem. Isn't F very much non-convex? Yes. Yes, I think it is convex because essentially here's a plot of F, right? This is a plot of F. This isn't convex function. I mean, the fact that it's like infinity here makes it sound like non-convex, but it is essentially convex. I guess, you know, one would have to define properly what convexity means if you have functions that attain the value infinity, right? I think that's what you want, but I would rather not go there because it would distract us from what's truly important. So Amireza says it's called extended convex function. Yeah. Yes, yes, yes. The simplex is a convex hull of coordinate spaces. Yeah, exactly. Yeah, yeah, yeah. Okay, so by the way, this extended convex function, I think you can find it also in optimization, you know, in optimization books. So at this point, what is this equal to? Can anyone tell me what is this equal to? By inspection, you can solve the problem. L infinity norm of positive components, exactly. So that's equivalent to saying it's equal to the maximum of Z. So let's define EI to be an indicator, like the canonical vectors, one-hot vectors. So it's the maximum over I of Z, of Z inner product EI, right? Which is equivalent to what Tristan says, which is the L infinity norm of the positive components. So in simple words, it's just the maximal element in Z, right? Maximal element in Z. So this was the F conjugate. Next, we want to calculate G conjugate, right? So what is G conjugate? So again, I need letters. What should be the letter? W equal to supremum. Let's use here U, I don't know, or V. Let's use V of W inner product V minus G of V, right? So this is again the definition of Fenchel duality, or sorry, Fenchel conjugate, not Fenchel duality. So let's just plug here the definition of G. So if you plug the definition of G, let us remind ourselves, what is G? G is the L2 norm, right, of a vector. So let's just plug here the L2 norm of V. At this point, what is the solution of this problem? What is the solution? What is this? So let me give you a hint. Let us divide this into two cases. Case number one is assume that the L2 norm of W is greater than 1. In this case, what is the value of this supremum? Plus infinity, says Tristan. But why? Why is it plus infinity? I feel like Tristan only knows that the conjugate of the L2 norm is an indicator, so he's applying a reverse logic. Oh, no, he knows the answer. Take V to be equal to alpha W and send alpha to infinity is the correct answer. Is the correct answer. So essentially what Tristan is saying is the following. Notice that here you have a choice, right? You have a choice of what V is equal to. So imagine that you choose V to be alpha times W, as Tristan says. What would you get? You get W multiplied by alpha W minus, and then here you have V, which is alpha W, right? Notice that this thing is equal to alpha W squared, L2 norm squared, I mean, minus alpha L2 norm of W, which is equal to alpha L2 norm of W multiplied by L2 norm of W minus 1, right? Now, what happened here? What is this thing? Now, notice that this thing is positive. Why is it positive? Because of this thing, right? Because it is positive, and obviously the L2 norm is positive, then you can just scale this quantity to infinity by increasing alpha more and more, right? So what we've done is construct a series of solutions which shows that this expression tends to infinity. I don't know what's happening with this thing. So we've constructed a series of solutions that shows that this objective tends to infinity, and therefore the supremum is infinity. So does anyone have any question about this case? Or is this clear? Or is it so unclear there's no even question to ask? Because that's always a possibility as well. Okay, so it's clear. The next thing that we want to do is consider the case where the L2 norm is less equal than 1. What is the supremum in such a case? 0, says Xiaoding immediately. But why? Why is it 0? Because you have x squared minus x, essentially. So notice that the answer 0 is a very natural answer. Why is it natural? Notice that this objective can be easily upper bounded using Cauchy-Schwarz, right? What does Cauchy-Schwarz say? It says that this is upper bounded by the L2 norm of W multiplied by the L2 norm of V minus the L2 norm of V, right? And notice, so this is just Cauchy-Schwarz, and notice that we know that the L2 to norm of W is upper bounded by 1, right? Yes, yes. Neo shows how simple this is. So if the L to norm of W is upper bounded by 1, then this becomes V2 minus V2, which is equal to 0, right? So the answer 0 looks sensible at the very least. The question is whether we can actually achieve this 0 objective value. And the answer is that we can, right? If you just take V equal to W, it should be V equal to W. I think it's, if you take V equal to W, V equal to 0. Yeah, that's one thing you can do. Yes. So you can just set V equal to 0. That's correct. So hopefully we're convinced now that this is G star. And notice that this thing has a name, right? What is this thing? This thing is simply an indicator of whether W2 is less equal than 1. Does this make sense? Because at least my indicators are always infinity or 0. It seems like some students have other indicators in their life. But in my life, I have only these type of indicators, unfortunately. By the way, a person who knows convex optimization could have said this just by knowledge, like previous knowledge, because if G is equal to an L2 norm, right, then it's immediately known that G is equal to the indicator of L2 norm less than 1. It's like one of those known things, right? There's like set of things that people know, so they don't like rederiving. So this is one of those things. So with those in mind, we're ready to go back to our proof. So what we're going to do is write here supremum over W. I'm not sure what it means, whack. I feel like, oh, okay, yeah. At this point, what we're going to do is we're going to insert the W conjugate, right? So if we insert the W conjugate, we get max over I, and then we need to do XW inner product with EI. Do you recognize this expression? Is this expression that you've seen, right? This is just this thing is this thing, right? The conjugate of F, right? This, okay? Now, the next thing that we want to do is plug instead of G, we want to plug the conjugate. So the conjugate was an indicator of whether minus W L2 norm is less than 1. So because I'm running out of space, I'm going to use this magnificent tool to put this down here. Okay, so we haven't done a lot so far. Okay, so now what we're going to do is just massage this expression until we get something that we like. So the first thing that we can do is notice that here there is an indicator and here there is a supremum. So this is equivalent to doing a supremum over W2 less equal. So first of all, you can remove this minus, right? Minus of L2 norm doesn't make sense. L2 norm of W is equal to L2 norm of minus W. So you can just remove the W. And second of all, this indicator, if this constraint is not satisfied, you would get your minus infinity, right? So the only way you would get the supremum is if this indicator is satisfied. So you can just write supremum over all the W which satisfy L2 norm of W less than 1, and then minus maximum over I XW EI, right? And now what we're going to do is, so does anyone know what's the next step? What is the next step? Yes, wow, you guys know what's up. Amireza says replace minus max with mean. Yeah, so basically we're going to put the minus inside. So there is a theorem which says that the maximum minus maximum of f is minimum of minus f, right? There's a theorem that says that. So if you do that, you get minimum of minus xw. Oh, by the way, everything, it should have been x transpose. That's a mistake. It should be in the Fenchel duality in the slides, x transpose as well. Oops. Right. So this is what we get. And then at this point, notice how this is almost it's almost something that we like. Why is this almost something that we like? Because this minus sign is kind of annoying, right? Doesn't it bother you, this minus sign? Don't you feel like it's unnecessary? Don't you feel like we could remove it somehow? Or no? Replace W by minus W, exactly, but is there a reason why we can do that? Symmetry, yes, exactly, symmetry. So by symmetry, what we mean is that notice that we're optimizing over the L2 ball or sphere, right? And if we're optimizing over the L2 sphere, then for every W, we're also considering the minus W. So there's no reason to do here a minus W, because you're maximizing over all W's which are inside a ball, right? Every W that you consider, you would also consider the minus W. I feel like I'm not saying this in the correct word. In this supremum, you have W's which are, let's say, on a ball, right? So for every W, you also have the minus W in this set, right? So there's no reason to write a minus because it doesn't do anything. You still consider the same set of solutions. Am I making sense or? Yeah, it does make sense. Okay, yeah. Okay. So at this point, we know, so Neo said that this looks like a max margin thing. And that is because this is a max margin thing. So notice that X transpose W, EI, is equivalent, it's equivalent to writing W transpose XI, or I guess we could write it as inner product, right? This is just by the definition of the matrix X. There's different ways to show this, right? So essentially what we've converged to, if you look at the whole derivation, what we've shown is that this quantity in purple, which is a horrible color because you cannot see anything, let's use green. So this quantity in green, which is the norm of the gradient divided by the loss, is lower bounded by the optimal margin. Okay? So we've previously denoted this by gamma star. It's max margin with all yi equal to 1. Exactly. Thank you, Amirasan. So this is the first sign that gradient descent or gradient is related to the margin, right? Because we have gradient, margin, gradient, margin. The next step is to utilize this relationship to prove that you converge to a max margin solution, okay? So the next step is going to be something you encounter, I think, many times in optimization. So it goes as follows. Imagine we look at the W at iteration t+1, and we write it as function of W at iteration t. How can we do that? How can we write how can we relate the loss at iteration t+1 with the loss at iteration t? What would be the usual Taylor? Wow, yes, that is correct. There's some optimization experts in the crowd. So we are going to do Taylor series, right? So in order to do Taylor series, let me remind you the following equation. WT plus 1. You see, this is why I shouldn't publish the slides. WT plus 1 is equal to WT minus, and then it's the step size eta t times the gradient of the loss at iteration t. Do you recognize this equation? Have you seen this equation ever? This equation is gradient descent, right? So it's actually GD, not SGD, but yes, close enough. So let me define this quantity here. I'm going to define as delta WT, okay? Delta WT is the gradient multiplied by the step size. So with this in mind, we're going to do the Taylor series expansion. So how does Taylor series go? Multivariate Taylor series says that we're expanding a function in the vicinity of a point, which is WT, right? And what we're going to do is we're going to add the gradient of the loss at that point multiplied by the perturbation, right? So inner product with the perturbation, which is delta omega t, plus, as Amireza says, we want the Hessian. So we will have the Hessian. So plus you have 1/2 multiplied by delta omega t multiplied by the Hessian, and then I'm going to leave some space here, multiplied by delta omega t. Now the Hessian is going to be evaluated at some point, WT minus, I guess, is it minus or plus? It's minus delta t, delta omega t. So what is written here? This is a second order Taylor expansion where beta is in 0, 1. So this is called the Taylor's remainder theorem. Exactly. Taylor's remainder theorem. So Taylor remainders theorem says that your Taylor series can be written as an equality as long as the final term of the expression is evaluated at a point which is between this point and this point. So essentially, this point is somewhere between, you know, let's say this is WT, and this is WT, let's write it, WT, let me check something, sorry, to make sure I'm not, okay, WT plus delta T, delta WT. So essentially, Taylor's remainder theorem says that Taylor series becomes an equality if you evaluate the highest term in a point between WT and WT plus 1. Does anyone remember such thing? Does anyone know? I do remember in my undergrad, I learned this last year in my calculus class. Okay, so if you don't remember, then then just Google Taylor remainder theorem, and you should see something that should make sense. Okay, so also if you Google this, this is a multivariate version. If you just Google the univariate version, it would be perhaps even clearer. So at this point, what we can do is we know that delta WT is equal to minus the step size times the gradient of the loss. So we get here the gradient of the loss squared, right? And then what we need to do is we need to somehow deal with this whole expression, right? So we need to somehow do something with this thing. So here's how you deal with it. Notice that half times delta omega t times the Hessian evaluated at some point times delta omega t is equal to, so what do we want to do? What should we do at this point? Does anyone have any suggestions? What should we do? What should we plug? What is clear to us? What would be the easiest next step? Transpose. Thank you. Yes, but that is not the next step, but it is a correction. So the next step is just plug in the definition of the Hessian, which we know, right? So we know the Hessian, based on some slide beforehand, is equal to sum over Ri xi transpose, right? So we just plug that in. And I remind you that xi is a vector and Ri is a scalar. Now notice that we have here two pairs. We have xi transpose delta omega t, sorry, delta wt, and we have wt multiplied by xi, right? So it's the same inner product. So you get half multiplied by sum over I from 1 to n, Ri times, and then you have xi transpose multiplied by delta wt squared. Now, what would be the next thing to do? Does anyone have any suggestions? I'm interested in upper bounding this quantity. So whenever we have an inner product, what kind of upper bound do we usually do? What's CS? Oh, yeah, Cauchy-Schwarz. Yeah, thank you. That is correct. So we're going to do Cauchy-Schwarz. Now, in the assumption of the theorem, we actually assumed that xi is less equal than b in L2 norm. That was one of the assumptions of the theorem. So this is going to be b multiplied by the norm of wt, delta wt. And notice that this is equal to half multiplied by, okay, so at this point, notice that this quantity does not depend on I anymore because it's the gradient, right? So we can actually take it outside and notice that this thing is just the loss. So this is the loss at the current iteration. Should it be, oh yeah, correct. Thank you. So this is the loss, and this is b squared, and this is the gradient of the loss wt L2 squared, and we also have the step size squared, right, from the delta omega t. Now there is a small confusing part here, which is notice that the Hessian was originally calculated at some point, which is between wt and wt plus 1, right? And so essentially, we need to calculate. So when we calculate here the loss, it should be at the point between wt and wt plus 1, right? And you can actually bound that above by the loss at the point WT. Because essentially the RIs are the loss, so the sum over RI is the loss at an iteration between WT and WT plus 1. So you can just upper bound it by the loss at the iteration T, because we're assuming that we're always decreasing the loss. Do any of these words compile or make sense? Or is this, if you don't understand this point, it's fine. I feel like this is a bit, so you don't have to assume the loss is decreasing. You can prove the loss is decreasing, but we're not going to do that because that's too much of a distraction at this point. Okay. I was thinking of adding it to the homework, but then I felt like maybe not. An induction argument on iteration. Yeah, the proof is very similar to what I'm going to show you. So essentially what we've obtained is that we can upper bound the second term with this quantity, okay? This is what we've obtained, plus. So does this make sense? As an upper bound, okay? So I should write here upper bound. Okay, so let me, does anyone have any questions on that last transition? Or no questions? Oops, what have I done? Move this bit down. Trying to get rid of this. Okay, so no questions. So the next thing we're going to do is we're going to take out the loss of WT. So we get 1. Yes, thank you very much. Thank you very much. Thank you very much. You're correct. Where does the second term come from? So the second term is from these expressions. So essentially, you start with this. Do you recognize this quantity? This is the other term. What other term? Do you mean this term? Oh, this term is from here because this is the gradient multiplied by delta WT, and delta WT is minus the step size multiplied by the gradient. So you have gradient, inner product gradient, right? That's the easier one. Okay. So at this point, we're taking the loss outside of the parentheses. So we get minus eta multiplied by the gradient of the loss, L2 norm squared, divided by the loss at iteration T, plus half multiplied by step size squared, B squared, gradient of the loss, WT, L2 squared. That's it. Okay. Okay, at this point, there is a bit of a non-trivial trick that one must use, but I think it's perhaps a common trick. The trick is that 1 plus exp of x, 1 plus x is less equal than the exponent of x. Okay, this is a trick. Now, if you use this trick here, what do you get? You get loss WT multiplied by, and then you get exponent of everything except the 1. So you get minus eta t times the gradient of the loss WT L2 norm squared over the loss at iteration t, plus, I'm just copying everything, it should be minus, plus, plus, minus, plus, half eta t squared B squared gradient of the loss WT L2 norm. Okay, just using this inequality. Now, at this point, what should we do next? Notice that we have here we have LWT on the one hand, right? In the, here we have LWT. On the other hand, we have here something that essentially depends on WT, right? So what's the logical thing to do next? Does anyone have any suggestion? Bounded by X max margin. Yeah, that's correct. That's correct. But I'll do that later. I'll do that later. But you're correct. Yes. So the logical thing now is to continue these steps in a recursive manner, so to speak. So if you've managed to relate LWT plus 1 to LWT multiplied by the exponent of something, you can now relate LWT with LWT minus 1, right? Just iterating these steps. So by iterating these steps, what would happen is you would get that this is less equal than L at step 0, the initialization, multiplied by the exponent of minus sum of S less equal than, this is supposed to be T, times the gradient of the loss, W at iteration T, L2 squared over the, it should be S, and I'm missing the step size, over the loss at W iteration S. Does this make sense? And here also sum. So I'm just essentially US2 squared. So does this step make sense? It does make sense. I see a note from Luke. So essentially what we're doing is we're saying here we had WT plus 1 and we managed to upper bound it with LWT and something else, right? So if you just repeat the same process, you can upper bound LWT as function of LWT minus 1 multiplied by an exponent, right? And then you can do the same thing many times and you get a bunch of exponent terms multiplied by LW0. And the exponents, if you multiply them, it's exponent of the sum, right? Does anyone have any questions? I'm not sure it's the time we open the confetti. That's what happened at the end of the proof. But okay, so if there is no questions, let me copy this whole expression to a new piece of paper. Okay. So this is LWT plus 1. So do you have, okay, so let me give you one step here. Notice that LWT plus 1 is related to something very close to a margin. So the loss as function of W is equal to the sum over I of exponent minus W transpose Xi. That's just the definition of the loss, right? So notice that you can lower bound the loss at iteration T plus 1 just by the maximum over I of the exponents. So you get minus, let's say, WT plus 1 inner product Xi. Okay, this is just replacing a sum with the maximal element. Okay, so at this point, can anyone suggest what would be the next step? What is a logical next step? what would be a logical next step? Take limits. Not yet, not yet. No. Essentially what we're saying is that the sum over I exponent W transpose Xi is lower bounded by the maximum over I exponent minus W transpose Xi, right? So you don't need the n. Okay. So what would be the next step? Let me make this perhaps, let's delete this part and make this smaller. Maybe it would make the next step clearer. Oops. What would be the next step? What would be the next step? So notice that we have maximum over I of exponent, and then here we have something that looks kind of like a margin, right? So don't you want to get closer to a margin? How do you get an equation that's talking? Yeah, we will do that, Tristan, that is correct, but subtract the margin. Take logs, yes, Jim Shaw. Thank you, Jim Shaw. So we just take log. So if we apply a log on both sides, we get maximum over minus WT plus 1 xi, and then we get less equal than log of W0 plus, and then what's inside here, this thing, right? Why can we take a log on both sides? Because log is monotonic. Because log is a monotonic function, if x1 is less than x2, log x1 is less than log x2, and the opposite. So what would be the next step? The next step is let's get rid of this minus, right? How do we get rid of this minus? Just by multiplying everything by -1. So if you remember, the max of max of minus function is equal to Oh, right. So max of a minus function is equal to minus mean of a function, which is equivalent to saying that minus max of minus function is equal to a mean over a function, right? It's just relating max and means. So with those in mind, if you multiply everything by -1, you would get mean over I, WT plus 1 xi is greater or equal than, and then I'm just going to copy these terms. So I want, oh, I think I should have had a minus here, right? This should have been a minus. So this is going to be here. And then I will have plus this quantity, and then the log W. Go away. W0, right? And I'm not sure about the sign. I think this should be a minus, but let me check with my notes. Let me check with my notes. Yes. And this should be a plus or a minus. It should be a minus. Okay, doesn't matter. Okay, so this is what we get, right? I just multiplied by a minus on both sides. Does this make sense? Does make sense. Now, what would be the next logical step? What would be the next logical step? So if you remember, our goal is to say something about a margin, right? margins are natural to talk to when we have something like xi inner product with w divided by the norm of w, right? If w is not normalized, then it's not as natural. Maybe a different idea would be normalize. Yes, normalize, exactly. But why do you want to normalize? Because essentially, if you implement this algorithm in practice, you can actually see that the norm of w is diverging to infinity. If you remember in the previous lecture, we saw this animation where the w was kind of drifting away, right? Because w is drifting away and you can actually prove that the norm of w is diverging, it makes sense to just normalize by the norm of w. Yes, in the theorem, it is normalized, yes. So I guess it would make sense here to normalize as well. But I'm just trying to convey some type of intuition for why you would think about this in the first place. I think the reason you would think about this is that, empirically you code this, in Python and you see something is diverging. So it makes sense to say, okay, how about we just normalize by its norm and study what is the direction converging to, if that makes sense. So at this point, what I'm going to do is just divide this by the L2 norm of WT plus 1 on both sides. So here I'm going to do divided by WT plus 1, L2 norm, and here as well. Now, notice that this expression here is beautiful because it shows us what is this quantity in a simple word. What is this expression in a simple word? This expression is the margin. Yes, thank you. Yes, this is the margin, right? And the right-hand side is, in some sense, it's still not perfect because notice how everything is written in terms of gradients, losses, and so on, except the denominator, which is in terms of WT plus 1, right? So you want to be able to represent WT plus 1 L2 norm using the other quantities, right? So how can we represent differently the L2 norm of WT plus 1? How can you somehow bound it? Does anyone have any ideas? I assure you, each and every one of you knows the bound. A simple bound. Triangular? Oh, yeah. What do you mean by triangular? Do you mean triangle inequality? Yeah, exactly. Triangle inequality. That is correct. Why? Because notice that you can write WT plus 1 as the sum, as W0 plus the sum of the step size t multiplied by the gradient of the loss at iteration t, right? This is just by the definition of gradient descent. You start from a point and then you modify it with gradients multiplied by step sizes. Now notice that this can be upper bounded just using the triangle inequality, right? So it's a bunch of triangle inequalities actually. Does this make sense? Do you like triangle inequality? It's useful. So what I'm going to do now is just lower bound this quantity by upper bounding the denominator. So because if we upper bound the denominator, we lower bound the whole quantity, right? Okay, let me just check something. 1 second. Okay. So here's what we're going to do. We're going to lower bound this. So we're going to write sum over s less equal than t eta s multiplied by the gradient of the loss ws L to norm squared divided by the loss of ws. And then this is going to be divided by, so I'm just going to use this inequality that we just had. So we're going to get w at iteration, this was w iteration 0 L to norm, plus sum over, let's write it as s less equal than t, and then it's eta t multiplied by the gradient of the loss ws L to norm. Okay, does this make sense? So I just lower bounded wt plus 1 using the triangle inequality. Okay? Yes, no, maybe. Maybe. Is there any question that would turn the maybe into a yes? Now, the other thing, I'm just going to copy it as is. Duplicate. Okay. Now, several times students have said that we can actually identify here so if you remember, we've proven beforehand that the gradient of the loss w, let's say s, L to norm divided by the loss ws is greater or equal than what? With the Fenchel duality, we've proven that this is greater or equal than gamma star. That is correct. Then the optimal margin, right? And so notice how this quantity appears here, right? Do you see how it appears? Isn't it magnificent that it appears here? Yes, okay. So once we plug it, we get essentially the last step, which is sum over s less equal than t. Let me push it a bit here. So here we have gamma star sum over s less equal than t multiplied by eta s gradient of the loss ws L to norm divided by the denominator, which I can just copy, and. What else? Oh, and the other quantity. Okay. So this is essentially the end of the proof. Why? Why is this the end of the proof? So if you look at the homework, in the homework, what you are asked to prove is that the sum over s less equal than t, eta s times the gradient of the loss ws L to norm is equal to infinity. Okay? What does it mean that this sum diverges to infinity? It means that this quantity is essentially infinity, right? This quantity is infinity, and this quantity is the same quantity, it's infinity. Now, what do we assume about W02? What does this quantity satisfy? It's finite, right? The initialization is finite, so it dies, as Neo says. It's rather violent. It vanishes. Yes. So essentially you have something that diverges to infinity divided by something that diverges to infinity, but plus something that is finite. So this whole thing converges to 1, right? Isn't this beautiful? So all you're left with is the optimal margin. Now, remember that we started by saying that the margin is greater or equal than this quantity. So if the margin of Wt plus 1 is greater or equal than the optimal margin as t tends to infinity, what does it say about this quantity, about this classifier? if I'm taller than the tallest person on Earth, what does it say about me? It says that I'm the tallest person on Earth, right? Yes, yes. So if the classifier has a margin which is greater or equal than the max margin classifier, then it has to be the max margin classifier. Now notice that we're neglecting another term here, and I'll get to that in a second. So essentially, this other term, in the homework, you're asked also to prove that S less equal than T, eta S times the gradient of the loss WS L2 norm squared is finite, right? So essentially what this means is that this quantity is finite and this quantity is finite, but this quantity is diverging to infinity, right? It perishes. What? Eta is also squared. Thank you very much. I don't know why I keep forgetting the square over eta. So essentially, if this is finite and this is finite and this is diverging to infinity, then this whole thing converges to 0. If this thing is finite and this thing is finite and this converges to infinity, this thing converges to 0. Okay. So this is the end of the proof. Does anyone have any questions? Yes, yes, yes. You can have that the sum goes to infinity, but the sum of squares is finite. Yes. How could a mortal? I was expecting, people in math to tell me, what is this trivial proof? Don't insult our time by showing us these trivial proofs. But you're saying this is a complicated proof. Oh, I'll get to that, Amireza. I'll get to that. I think I'll get to what you're asking. How does a mortal come with such a proof? LOL. Basically, there's some history to max margin classifiers. It's not like one day someone wakes up and they say, Fenchel duality it is, right? There's history of people who studied max margin classifiers and who know under which conditions they arise, right? So if I were to explain the history, it is likely that you would think this is, it's more reasonable a person would come up with such a proof. And when I'm referring to the history, I'm actually referring to, there were works on an algorithm called boosting, which are highly related to this type of proofs. Amireza says the most non-trivial step is the exp. Yeah, this step essentially. Yeah. Okay, so at this point we have proven the theorem. I've written the proof in 3 concise slides written with a beautiful font, not like my ugly handwriting that you can look at later. And if you remember, I mentioned that there were 2 papers by Nettie Srebro and co-authors. So the other paper, which is called The Implicit Bias of Gradient Descent on Separable Data, actually did a much more refined analysis. What does it mean, a refined analysis? So here's a theorem from their paper. So they say for any data set which is linearly separable, so now you know what linearly separable is, and any smooth decreasing loss function, so you can just replace these words with exponential loss, with an exponential tail, any step size eta, which is less than this quantity, and any starting point W0, the gradient descent iterates will behave as Wt equal to W hat log t plus rho t, where w hat is the L2 max margin vector. So essentially, what you have here, this is essentially a different way of writing a max margin classifier, okay? And what they're saying is that the classifier that gradient descent, so this is gradient descent, is equal to the classifier of the max margin, so this is max margin, except that you have here a scale log t, which means that the norm of the max margin classifier increases at rate log t, and there is a certain perturbation rho t, okay? So based on this equation only, essentially what you can tell is that the rate at which the norm of the classifier increases is log t. Makes sense, the gradient of Wt is of order 1 over t. Yeah, I think it does. I think it does. I think it does. But maybe we can discuss that at the end of the lecture. But I think it makes sense what you're saying. So they continue saying that the residual grows as rho of t is equal to log of t. So essentially rho of t is very small. And what this means is that as t tends to infinity, your w tends to w hat, which is the max margin classifier, if you just normalize both things. And they're also able to prove that the residual is in fact bounded for almost all data sets. So how is this theorem different than the theorem that we have proven together? This theorem is essentially telling you explicit rates, it is called, explicit rates. Rates of what? Rates of growth of the norm and rates for the residual, like how big is the residual, how big is the deviation between the max margin and the classifier. And they have other theorems. So this is related to Gina's question from the previous lecture. So there's a question, what does beta smooth mean? The gradient is beta Lifshitz. Yes, I believe it does. I believe it does. I believe it does. But I don't want to say 100%, but I believe it does. This is also very standard assumptions, by the way, in the optimization theory. So in the previous lecture, Gina actually asked, how do you generalize this result to multi-class classification? So there is a theorem in their paper which says for multi-class classification, your classifier, this is the classifier of gradient descent, is going to converge to a multi-class max margin classifier, which they denote by W hat. Okay. What is W hat? W hat is the solution to what's called K-class SVM. So I assume not everyone knows what SVM is. So let's just try to understand what's written here. Okay. So essentially what's written here is that instead of having a margin, which is W trans, let's say W inner product Xi multiplied by Yi, which was our original margin, right? Do you remember this? In this case, what you have instead is margin is defined to be W of a certain class C minus a different class C prime inner product with Xi, where here we're saying instead of, let's say, Yi. This is defined to be the margin. So what does this mean in simple words? In simple words, Xi is your example. Yi is its corresponding class, right? Xi, Yi is a tuple of an example and a label. Wi is the classifier which corresponds to the correct label, right? And Wc prime is a classifier of an incorrect label. So let's do an example. Imagine that this is an image of a cat, We like cats. WYI is the cat classifier. And WC prime is the dog classifier. This is the margin. Does this make sense? So instead of having an inner product with a classifier, you just compare. So in the context of a deep network, this is extremely simple to explain. Does anyone remember what is a logit in a deep network? Do you remember the logits of a deep network? The logits were the output of a network, which were of length number of classes, right? So imagine you have a logit and you have several classes. So for example, this corresponds to a cat and this corresponds to a dog. So the margin is simply this thing minus that thing. It's X minus Y, right? Because in the case of a deep network, these entries would be the classifier of a cat multiplied by some feature vector from previous layers. And this thing would be the classifier of a dog multiplied by features from previous. Okay, so that's a good question. How can you choose NEC prime? Yeah, oh, sorry. So, and you can choose NEC prime for WC prime. That is exactly correct, yes. So the goal of max margin in multi-class classification is to maximize the minimal margin, where the margin is defined with respect to all possible class pairs. And of course, you don't want C and C prime, YI and C prime to be equal, because that doesn't make sense, right? If C prime is equal to C, then it's just 0. So the quantity is meaningless. Does this make sense? Okay, so here you can see, so you might ask yourself, you don't understand the optimization problem. How do you determine C prime? So first of all, in order to determine C, you don't determine C prime, you're trying, so, okay, let me explain the answer to both questions at the same time. What does this expression say? This expression is looking at W of the correct class, right? And this is W of a different class. So in my language, this would be C prime, right? And they're looking here for all C primes not equal to YN, right? So essentially, you have a set of margins for all the C primes which are not equal to the correct class. So you don't determine C prime, you have a bunch of different C primes, and you're interested in maximizing the margin with respect to all the C primes. Does this answer the question, Karen? So part 2 says, do we calculate the margin for YI and the rest of classes we have? Yeah, essentially, I usually write it in a different manner, actually. I like writing it as follows. I usually like denoting my examples as XIC. So XIC is the ith example in a certain class, right? So you can imagine like X1 dog, which means the first dog, X2 dog, X3 dog, and etc. And then the margin would be WC minus WC prime XIC. I find this more pleasing to look at it this way, right? And then you're essentially interested in all the cases where C prime is not equal to C to look at the margin. Because for C equal to C prime, this is just 0, right? Reza says, I don't understand the optimization problem. So this optimization problem is trying to find a set of classifiers W1 through WK, which are minimizing the L2 norm and which have a margin that's greater than 1. That's what this optimization problem is doing. The one is rather arbitrary. It doesn't matter what scalar you put there. It doesn't matter. So, okay, you cannot put 0 there. I guess it has to be positive, yeah, but maybe that's a better description. So at this point, I just want to finish this slide and then I'll finish the lecture. So at this point, you should ask yourself, why are we talking so much about logistic regression? How is any of this related to deep learning, right? Shouldn't you ask such a question? You should ask such a question. And the way this is related to deep learning is that the final layer of a network, as I might have tried to explain in the previous lecture, is equivalent to logistic regression, multinomial logistic regression. And so based on this theoretical work, what would be a reasonable hypothesis to make? Does anyone have any suggestion for a reasonable hypothesis to make about the behavior of deep networks? Does anyone have any hypothesis to make? No hypothesis. Just any hypothesis would be fine. You can assume what you want. The hypothesis I'm thinking of applies not only to fully connected. Exactly, yes, thank you, Neo. Neo, did you read the final presentation slide? Yes, yes, that is correct. So, yes, 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 okay, that's good. That's exactly correct. So Neo is saying the last layer is doing the max margin thing, like a way to explain why you can keep increasing test accuracy even when you have achieved perfect training. Exactly. So essentially, if you remember, we started this whole lecture, in the last lecture, we started the lecture by saying how the training error stops improving at some point, but the test error keeps improving and improving, right? So we now understand that at a max margin classifier, right, is essentially explaining how you might improve your classifier past the point of linear separability, right? Linear separability is just when you have something like, this is linear separability. Max margin is picking a very specific classifier that is likely to achieve better test error. And so essentially what this work of Nati and co-authors was trying to say is that if you train gradient descent on separable data, not only will it be able to classify your data, it will also converge to a very specific type of a classifier. And so again, I ask you, what is the prediction based on their work? What would be the prediction to make? The prediction is that the last layer of the network, the last fully connected layer, which is analogous to multinomial logistic regression, is doing a max margin classification. Now, if you do an experiment and you would not get that, you would be very confused, right? You would be very confused. Okay, so let's leave it at that. So this is the end of the lecture. Thank you for joining and see you. It is a hypothesis that will be refuted, or maybe not refuted. You will see. I don't want to spoiler. I don't want to spoiler the course. Let's keep it at the hypothesis, which is to be checked. Yeah, that's part of the narrative of the course. Exactly. There's a plot twist. There is a plot twist.
Can I ask a general question?
Yeah, of course.
So basically right now it's like we have a lot of empirical observations of how things work, and then you're just formulating like scientific hypothesis of why these things work, and then uh, it's kind of like when you're doing physics, kind of. So the
Yeah,
mindset here is not that you want to come up with a unifying theory of everything, but then instead you study, let's say, thermodynamics, and then you have a lot of observation of how things, and you try to explain, for example, why like heat flows from hotter regions to
yeah,
cooler regions, but and then you build a mathematical model like
yeah,
this one that try to explain it, and then you realize whether or not the evidence actually. So that's the kind of the mindset to have when
yeah, yeah, yeah.
learning about this course.
Yes, exactly. But notice that the name of the course is Deep Learning Theory and Data Science, right? So the data science part is supposed to find empirical phenomenon of interest, right? For example, like this phenomenon of interest, right? This is a phenomenon of interest that is the result of data science, of running experiments. So the course is also about finding phenomenon that are interesting.
I see. That makes sense. Thank you.
How did linear separability come into the proof that we did today? That is a good question. Hmm. Let me see. There's actually a way, by the way, to generalize this to nonlinear separability. And there's a work that did that. So you don't actually need linear separability, but I believe the assumption is needed here. Let me just think, where exactly is it used? Where is linear separability used? When you neglected the effect of yi, isn't that because of linear separability? Not quite. Oh, Karen is saying that something in the problem set touches on it. So it's possible that this part of the proof does not use linear separability, but in order to complete the proof, you need linear separability. By the way, the the linear separability is essentially equivalent to saying that all the W transport T plus 1 XI are positive, right? So I think that's like if you trace the proof and find a place where we need them to be positive, that would imply we need linear separability. But from the top of my head, I cannot see here where exactly is it used. But that's a great question.